Can I use this mic? Hello? Does this work? Great, this still works. Sweet. All right, so, so in the next 20 minutes or so, we'll deeply dive into resource plasma and how it relates to sort of the existing plasma constructions. Just a quick show of hand. Who here remembers sort of plasma cash, plasma debit, 2017, 2018 plasma research? Anyone? Okay, there's so much cool content on plasma because we've been thinking about this problem for a while. So if you ever want to learn more, really go back into some of the old material. Because this is, and the nice thing is this generalizes a lot of sort of the current concepts around rollups and L2s that we have at the moment. So I will briefly cover what is plasma, some of the problems that exist with plasma at the moment, specifically around you need specifically identifiable owners for every resource within plasma in order to actually for this construction to work. Then I'll cover what the Anoma resource machine is and how it relates to plasma and like sort of state layouts. Then what is resource plasma, and then what are the hard problems of plasma, and not really only what are the hard problems of plasma, but what are the hard problems in general when it comes to these type of scaling solutions, and this also includes rollups. And to a large extent, resource plasma makes a lot of these sort of like hard problems very obvious because it's a very generalized framework to think about things. Yes, so what is plasma? Well, plasma really, this is probably the most recent overview, which I would recommend as an intro, which also has all the backlinks to like MVP plasma and so on. It was this great post by Vitalik in November last year, which really talks about plasma with ZK proofs and hints to the return of plasma. We'll get there eventually, I think. The massive resurgence of plasma hasn't yet happened, but we'll see what happens. So, what is plasma? The TLDR. It's a family of scaling solutions within our ecosystem around how can we get more throughput for actual end users or applications that inherit some amount of security from the main chain, right? And ideally, it requires only posting deposit transactions, withdrawal transactions, and updated state routes to the main chain. All the sort of extra data in compute is kept off chain. And really, I want you to always think about data. Data and state is the fundamentally hard part. Like scaling compute works reasonably well. Scaling state and state access and sort of state distribution, that is incredibly challenging. And so what is actually the main difference between plasma versus sort of the existing rollup constructions? Well, the main difference is that the current rollup constructions post their data to the Ethereum main chain. And in plasma, you do not have a specified sort of data availability layer. So really, rollups, there's a specific single DA layer. In plasma, you could have a single DA layer, but it's not encoded in the architecture. So if you wanted to, for example, outsource this to Google Cloud as your DA layer, you could do this with plasma. And this is like none of the other things around compute or proofs or compression really matter. Like the fundamental difference between plasma and rollups is that in plasma, you do not have a specific single DA layer, and you can much more flexibly design your system. Like every user keeps their own state rather than all of us posting this to the main chain. So with this, and really this is, from a scaling solution, this was actually very useful, like having Ethereum as a single DA layer, because it means that we have this logically centralized place that we can just all agree on. We inherit the sensitive resistant properties around data withholding, because the Ethereum validators will most likely keep serving us the data. But we can also think of like, well, what are other places where we could be storing this data? Cool. So with that, let's go through some of the key concepts in Plasma. And really, the first one is the operator. The operator produces blocks. It publishes once in a while some state routes for each block to the main chain. So for each Plasma block, the operator publishes some state route to the main chain. And crucially enough, in a rollup, the operator would send the data to the main chain, nowadays as blobs, in the past as transaction call data. And in sort of the true Plasma construction, the operator would send the data to the individual user. So like you can think of this like I own a small piece of state, and when I send a transaction, I update the small piece of state. In sort of a rollup world, this data gets posted to the main chain. In a Plasma world, this data gets posted to me, and I am now responsible to keep this data available for myself. I, of course, could also then decide that I myself want to post it to the main chain, because I don't trust myself with sort of like keeping this data on my local device, right? You get the sort of all the flexibility here. Yeah, and then the commitments are really just the Merkle roots, which sort of attest to the state of the system that I can then use to reference, well, my data that I have locally. I construct the Merkle proof, and I can find sort of the Merkle path on chain against the Merkle root that's actually stored within the contracts. Yes, the other important concept is withdrawals, because we wanted to make this, the idea was always, how do we make a trustless scaling solution where even if the operator faults or the operator goes away or the operator tries to cheat, how as a user can you still remain safe? And really this is like, yeah, if the operator misbehaves, you as a user can directly publish the data that you hold to the main chain as a proof that you actually own this data, and then you get access back to this data. And we'll come, and I'm speaking here very much about data. In a sec, I'll talk more about specifically sort of applications need to assign semantic meaning to data. If we just talk about this as data in the abstract, then actually all of these problems are a lot simpler. But like state here means, or data means, like for example, I've been paid. Like these are my assets that I hold, or like I hold a CDP in Maker. This is the kind of data state I'm talking about here. Yes, and then the idea is that, well, if I can execute a forced withdrawal, because the operator may be like not alive anymore, so I can submit my state plus a proof to the main chain to withdraw my own personal state. This were the original sort of like Plasma in the early days had a 7-day withdrawal period. During that 7-day withdrawal period, users could challenge whether the state updates were correct or the proofs were correct. So specifically, users could challenge that they had to keep watching that maybe someone else tried to withdraw my assets, and then I had to prove from a previous state, right? Like think of this at block 1,000, someone sent me some funds, and now we're at block 2,000. That user had always the ability to go back and claim, well, at block 1,000, that's actually the latest state, I own these assets. And then I had to keep watching the chain and go like, well, no, you've like transferred that state to me, I now own the state, and so I have to challenge this during the challenge period. You had to challenge whether you had a double spend or whether the actual, like the end state currently was the result of an invalid history. To most people, this should look very familiar to optimistic rollups and fraud proofs, fundamentally because they are very similar concepts. Again, the main difference between this kind of like optimistic Plasma versus an optimistic rollup right now is where does the data live? This is sort of the, this is just the very fundamental, like these are not two distinct concepts, they are very closely related with each other. One of the nice things about Plasma is that, in the original constructions, it was always designed as like, how do we scale payments? It was, and this works really well because we can have a very simple state layout for sort of payments because there's always a specific owner that's attached to some coins. This generalized model does not work super well for sort of generalized state. And we're also seeing this right now with the optimistic rollups that like making generalized fraud proofs for the EVM is actually very, very difficult. Then we have this other type of Plasma, which is Plasma, but with validity proofs. And validity proofs are real just your knowledge proofs of correct execution of some state transition function. Right? You could think that this is like a ZKVM, for example. This is sort of like a validity proof. And here the operator actually in each new state, they submit a zero knowledge proof that proves correct execution, that as a result, we do not have the problem anymore that the operator may have just like committed an invalid state transition where they send all the funds to themselves, because that's not possible. You cannot generate a zero knowledge proof like that will correctly verify. And as a result, we can process withdrawals that refer to the latest state root immediately, because we know, well, the latest state root must be a valid state of the system because we verified the proof for it. And so if I want to withdraw from the latest state root, I can do so immediately. And again, these are not entirely dissimilar to a ZK or succinct rollups. And here really the only fault that an operator can commit is they can withhold data. So they can actually not send you the data anymore so that you cannot construct these proofs yourself. But they cannot, for example, take all your funds. So what are the advantages of Plasma? Well, The main advantage really versus a rollup is that you do not have to publish all the data to the main chain. And yes, this has gotten a lot cheaper with blobs recently, but still sort of fundamentally, rollups are not a true scaling solution because like the amount of data that a rollup has to publish to the main chain is going to be proportional to the amount of usage you have. So like for a true scaling solution that goes to billions of people, you would actually want something that's constant in size, right? That like no matter how many people interact with the system, I have to publish a constant amount of data to the main chain. And yes, so with Plasma, the really clever thing is that we can probably get to a point where we can publish constant amounts of data that needs to be published to the main chain, regardless of the actual user throughput. Yeah, this is the hot take that really, if you look at the requirements for scaling Ethereum as, well, we want to allow unbounded user interactions with a constant cost on the main chain, plus we want to give the ability to users to have some security guarantees coming from the main chain, then rollups are not actually a true scaling solution, and Plasma is sort of the only scaling solution available that gives us constant cost scaling on the main chain. So in that sense, rollups are really rather a like heterogeneous execution charting design where like you outsource a lot of compute to some sequencers, to some operators. And by the way, you can also like see whenever you hear operator on Plasma, think sequencer on rollup. They're like exactly the same thing. They're like someone that does some compute and like does some ordering and yes, does some sequencing and execution. Cool. So coming to some of the problems with Plasma and how can we tackle them to actually make this a reality? Or like how does Plasma, resource Plasma, try to tackle some of these problems in order to give us this kind of constant scaling factor? Well, the first problem is dependency tracking, which is really like how do we track state across blocks on the main chain. The next thing is developer-facing complexity, and then the really hard part is incentive-compatible generalization, which very fundamentally depends on sort of app semantics, on what applications, what semantics applications assign to their state. And I'll go through all of them here. So dependency tracking. The EVM does not attempt or limit state dependencies. As in, if I'm currently in block N, my ETH could have come from any other account in the system, like a million different accounts in block N-1. So there's no sort of direct, where it's like, oh, this coin moved to someone else. This is like, it could have come from anywhere in the past state. This makes it very difficult to build systems with this. Because exiting could possibly require the publication of the entire history of that state. And this is recursive when you think about it, right? Like the state at N-1 depends on fully the state at N-2. And so we are fundamentally limited here by the throughput of the underlying of the main chain in terms of being able to handle processing all that history. And as a result, we can probably not run sort of the naive Plasma implementation as a like incredibly scalable version because we have to slow it down to account for, well, we may have to run exit challenges from time to time. Yeah, so in the worst case, the exit game would likely entail limitations on the compute and storage bandwidth of the main chain, or of Plasma, since we must be able to post all the data to the main chain. And fundamentally, optimistic rollups have exactly the same problem. This is like, they are also not magic. Every time you actually have to re-execute something on the main chain, you kind of start running into this problem. The other thing is developer-facing complexity. Plasma works well with state objects that have clear owners. Like think if I hold an ETH, that is a clear owner, I can always withdraw this back to the main chain. This becomes a lot more complicated when you think about this as like a Uniswap contract. Like who is responsible for the state of the Uniswap contract? How do I, maybe as a user, I would want to withdraw the entire state of the Uniswap contract to chain because I've been wronged, right? But now I can then have the ability to force every other user of Uniswap to also be like, sort of have to go back to the main chain. So this is, Plasma works really well for things that have clear economic owners, and it's kind of unclear how to adapt the incentive model for objects without clear economic owners, and we'll actually go through the example of a CDP with Maker here in a sec. But it comes down to like who should publish or store the data. So coming to the incentive compatible generalization, this is the third problem we're facing at the moment. Plasma application developers must actually reason about who owns the state, like who is fundamentally responsible for the state, and who has the right incentives to store it as well as publish it. Because it's not always that you may want to publish your state, and we'll see this at the CDP example. Again, all these problems also apply to specific rollups, and we've just solved them by always just using the Ethereum main chain as the sort of canonical data availability layer. But again, this doesn't really scale that well. So what does it look like? What does resource Plasma actually look like? So before this, we sort of went through sort of some of the problems of Plasma and the history here. But what does it actually look like to have something called resource Plasma, which is a combination of the Anoma resource machine plus Plasma? And yeah, so if you're not familiar with the resource machine is an alternative state architecture for Ethereum. It's something you can deploy on top of Ethereum. It's kind of like a virtual machine, except it's not. It's more like an intent machine. You'll see in a sec why. If you want to read the full specs to this, because I'm running slightly low on time, you have 15 seconds to scan the QR code. It's fully specified. The TLDR, to a large extent, is the Anoma resource machine just focuses on state layout. It does not care about the instruction set, or does not specify a fixed instruction set or a fixed message passing model. Yes, so the EVM actually bundles 3 different things. And this is generally true for all VMs in the space right now that bundle 3 things. They bundle the state architecture, so how state is stored, accessed, permissioned, how do our writes and reads handle to that state. For example, like the store, the load instructions in Solidity are like, they're the state access. It bundles the instruction set. So how is computation actually performed? This is like, you can think about this as the specific like add, multiply operations in the EVM. And then it also bundles the message passing model. So how do different programs interact with each other and pass data and messages to and from each other? And the Anoma resource machine unbundles this to a very large extent, which is it only cares about state. And state is split into resources that are each associated with the resource logic, which defines the permissions for updating the resource logic. And resources are only ever created or consumed. They're never modified. So you can think of this as a resource UTXO model. Yeah, resources are immutable. They're only created once and consumed once. The instruction set is really an implementation choice. It is different resources can define different instruction sets in order to modify their state. Resources only care about state. And then the message passing model is very much determined at runtime. For example, in the intent-centric world, that a number of intents get float around, the solver combines all of them, and then the solver sort of in their specific execution path decides how these resources interact with each other. But the update on the Anoma resource machine is just sort of like, this is the old state and we're going to this new state now. Yeah, so how is this actually done? Well, the Anoma resource machine has the state can be understood as 2 things, which is really 2 nullifier sets. So you have the commitment, you have the commitment tree and you have the nullifier set. The commitment tree tracks all resources that are created, and the nullifier set tracks all resources that have been deleted or like have been consumed. If you're familiar with the Zcash or like generally circuits, this kind of structure will look very familiar to you. Yeah, and once you consume a resource, the nullifier is added to the nullifier set. So yeah, what is the basic idea with the resource Plasma? We can build a Plasma-like construction on top of the Anoma resource machine, deployed to the EVM on Ethereum. And this gives users the access to this kind of state architecture in order to build incredibly scalable sort of applications on top of this, but this doesn't come without costs. So operators here, the operator executes transactions and publishes only the Merkle roots of the commitment tree, as well as the Merkle root of the nullifier set, and approve of correct transaction execution of all the transactions that were included here. Again, clients here need to start storing their own state. The state is not necessarily published by the operator to the main chain, albeit that is a possibility. If you just want to do the trivial thing and just dump everything in a blob, you can. Withdrawals are handled that effectively users would make a proof against the latest nullifier set, and then they can be processed immediately because it's a ZK construction. So we know that the state is valid. And when a user makes this kind of proof, they reveal the nullifier of the resource being withdrawn, so they can't withdraw it twice. And again, a resource here can be a very complex state object. It's not necessarily just it's a coin or an asset. It can be a very complex piece of state. Yes, in case the withdrawals, in case the operator actually withheld a bunch of data and didn't send it back to the user may have to act on an old Merkle root, and then you still start the same kind of challenge game where I will submit a proof against an old nullifier set that I want to withdraw the resource. And here again, you need to give it a little bit of time for anyone else to be able to claim, well, no, the new nullifier set is he's actually already withdrawn that resource before. Yeah, and if no conflicts are found, then the sort of withdrawal can happen. But the nice thing is we only have to actually check for for multiple withdrawals or double spends, because again, it's a ZK system. The client only needs to store their personal resources. So the client doesn't need to store the state of the entire system. They only need to store the resources that they care about, plus some associated linked data. Then proofs that the commitments correspond to these resources are included in the actual commitment tree on chain. And again, we've already spoke about the nullifier set. And the nice thing is, from time to time, clients could decide to sync, and then they just sync the latest nullifier set in order to make the proofs quicker, like if they want to do immediate withdrawals in the future. Yeah, the clients wanting to withdraw immediately must update the proofs on chain. And this is the option you have to take if the operator withholds the latest data. Okay, so we went through some of the problems with Plasma, and we spoke a lot about state so far. I would say that sort of dependency tracking is mostly a solved issue, because the Anoma resource machine has this very nice generalized state abstraction that allows you to very easily be able to track individual pieces of state rather than global pieces of state. And fundamentally, this is also by far the most scalable model, because it means that rather than all having to run this kind of global database in the middle that we must all sync to, every user just keeps their own state, and as a result, we get this very nice scaling property where we don't have to design a global database. We can rely on many individual edge devices actually holding individual pieces of data, and only when needed do we have to reveal it. And I do not have to care about anyone else's data in this room, and so my local syncing is super, super fast. So with developer complexity, applications have to be redesigned for this new state architecture. There's almost no way around it. Maybe we can think about compiling the EVM to this kind of model. So running this kind of model on running an EVM compiled to this model on the EVM. There are going to be performance trade-offs, and it's mostly going to be easier for people to actually redesign their applications around this kind of state model. The incentive compatible generalization is actually very tricky. And we'll see this actually, I'll skip through this slide, because the CDP example is very easy. So in a CDP, like a Maker CDP, I may create a CDP, and if this is in the green, I do nothing, and then, or if I want to withdraw from in the green CDP, I will reveal that state. But if it's in the red, I actually personally do not have any incentive to reveal this, because I'm much better off that we lose this piece of state. So in some applications that require complex shared state, there's probably a hard requirement that there's sort of a neutral third party that holds this kind of state. And for example, currently this neutral third party is the Ethereum main chain validators. The nice thing is, even Maker has actually a governance system. So there's an obvious point where there's a very good token model that maybe the token holders of Maker should be running this kind of application-specific DA, because they fundamentally care about the health of Maker, right? And so they can run this application-specific DA. This makes the token a lot more sensible, rather than just being a governance token. Now actually provides utility to the system, and this utility is fundamentally needed from an architecture perspective. There's no way to design around this. Someone must hold the data that's neutral enough to care about the overall health of the system, rather than individual actors within the system. The nice thing is here that the resource machine makes it very easy to designate who should store what state, but it doesn't change the fundamental design problem, the game theoretical design problem. But this is also true for every other constructions out there. It just, this model makes it very obvious. Okay, quick conclusions. Oh wow, I'm definitely over time. So the resource model is helpful for Plasma because it like makes the state layout very clear, but it is not a magic thing. Like, it is not the thing that's going to solve all our problems. We actually have to very deeply think about who is responsible for what piece of state. But at the same time, it is also a very scalable way to do this. So this incentive design problem is not something that actually can be solved at the architectural level. This is something that needs to be solved for application developers when they think about the semantics of their application state. The other cool thing is that rollups really are just specific instantiations of Plasma, where instead of rollups store the state all on Ethereum, with Plasma you just get more flexibility here. There's also a ton of other problems around sort of like challenges you think about, like about clients keeping their own state. Are all clients always are going to be capable to back up their own state, to maintain their own state, right? Like, for example, in Zcash, by default, every wallet dumps their local private state onto the Zcash chain in order to make it retrievable later on. But here, users could even decide that they want to encrypt their state and drop it on AWS. The model just gives you that kind of flexibility. And again, the limitations of where state's stored are fundamental to all these applications. Yeah, so really here, this is an attempt to sort of reinvigorate the Plasma debate by combining Plasma plus a resource machine and see where we're getting to. I actually personally hope that we spend a lot more time on Plasma again. And if you're interested in joining the discussion around Plasma, it's about halfway through this post. I'll leave this up for like 15 seconds before I'm being kicked off stage. Yes. So yeah, thank you very much.